Hello. At last class, I discussed uh, the derivative concept and give the definition of derivative, which was this tag, that is this one, a mathematical definition of derivative. Derivative itself, a mathematical terminology, but we saw that it has geometrical theme, okay, which is in fact slope of the function or slope of the tangent lines, and it has its physical theme. This is in fact physical theme, then physical theme, okay. This is which is instantaneous rate of change, and economic theme, okay, economic theme, we can see this is marginal concept. So it has also humanistic approach. We can say humanistic approach, we can say as responsiveness, okay, responsiveness, or reflection, okay, responsiveness, okay. So I will give you a good example now, how this derivative concept, this mathematical term, yes, derivative concept, is play a very important role in decision making in everyday life. Okay, so let's see. Okay, I have a data. COVID-19. Today I took this data from WHO. That is COVID-19 data weekly in Bangladesh. Okay, if you see here, number of weeks. Okay, I have taken here 4 weeks of March and 3 weeks of April. Okay, that is infected cases, that is COVID infected cases, okay, thousands in thousands, and second column is infection rate, okay. Infected cases in absolute volume, okay, absolute quantity, which is so COVID cases, positive cases started sharply increase in from 1st March. Okay, at 1st March, COVID infected case for 1 week. Okay, for 1 week it was 8,000, and with compared to previous week it was 67% infection rate. Okay, second week, this is 12.5 thousand, and the infection rate was 91%, okay, per week. Okay, third week 23,000, infection rate was 85%. Fourth week 34.5 thousand, 66% infection rate. And at 1st April, infected cases was the highest, 48.7 thousand, okay, but infection rate was 26%. And second week of April it was 36.3 thousand, and infection rate was negative 25%. Third week, 27,000 cases was infected people, and infection rate again minus 25%. What we can see when we see here in absolute volume, yes, number of people infected. Suppose if we take third week, okay, third week of March, and suppose third week of April, what we can see at third week of March, infected people was 23,000. At third week of April, 27,000, 23,000, 27,000. What we can say? We can say situation that is increases number of infected people. Okay, if we take suppose fourth week, here 34.5 thousand, and second week of April we can see 36,000. Again, number of affected people increases. So we cannot say here anything, but if we compare this, if we compare the rate of change, that is per week rate of change, we can see suppose second week of March, 12.5 thousand, and in April 36,000, again increase. Now yes, that is, we can see here 91% infection rate increases. Okay, third week 85,000%. Here third week 85%, but in third week infection rate minus 25%. That is, infection rate decreases. That is, situation is getting better. Okay, fourth week 34.5 thousand, and here suppose second week this is 36,000. It seems to be worsening, but if we see the infection rate, here we can see in fourth week this was 66% infection rate increases, but here we can see minus 25%, that is decreases. Okay, infection rate decreases. So if we want to compare and make decision, absolute quantities do not say anything. Okay, we cannot make decision. Okay, in so but when we see the infection rates, it says about the comparison, that is, we can say whether situation is getting better or worsening. Situation here we can see situation, COVID situation is getting better in April, first, second and third. Okay, from second week we can see, or from third week we can see even infection rate decreases. Okay, decreases. Even from March third week infection rate decreases. So if we let y equal to c of t, COVID function of time, then that is, infection rate is defined as y derivative, that is c prime of t, that is dy by dt. Yes, infection rate per week. Okay, and depending on which we can make a decision, that is, somehow this infection rate started decrease, that is, it was lockdown. Okay, and some measures was taken by government, and we can say that that measures was effective. Okay, so as situation getting better. Okay, so every time we can make decision by derivative. Okay, or by instantaneous rate of change. So without rate of change concept, we cannot compare and we cannot make decision. We cannot choose the best, or we cannot optimize our decision. Okay, so I think you understand it. Okay, roots and discovery of calculus. Okay, calculus, that this is a Greek word. Okay, which means calculation. So calculus started its journey from Archimedes. Okay, but modern calculus started its journey at the 17th century by Newton and Leibniz, and by discovering the fundamental principle of calculus. Okay, So from Archimedes to Newton, it's in fact 18th century. Okay, in fact 18th century, there was in fact no significant development in sense of four major mathematical problems. In fact, this is, these were in fact tangent lines problem or slopes problem, that is how to find tangent lines for a curvilinear function, or area problem, area of a general region and length of a general curve. Okay, general curve, and volume of a general solid. Okay, these three measurement, and how to maximize or minimize of a quantity again, and how to find velocity function and acceleration function from distance formula or position function, and converse when given suppose position function, how to find velocity function and acceleration function. So these four major mathematical problems were undiscovered. Okay, over 18th centuries. Okay, they don't know how to solve these problems. So after discovery of the calculus, that is give Newton and Leibniz in fact discovered the fundamental relationship between in fact two parts, no? Okay, two types of problems. Okay, one is differentiation problem, another is integration problem. Okay, and what was the differentiation problem? That is tangent line problems or slopes problems, how to find tangent line or slopes of a curvilinear function. Okay, and integration problem was how to find area or area function under a curve. Okay, and this problem in fact we can otherwise say that how to find instantaneous rate of change. This is physical theme. Okay, so physical problem. Okay, and another integration, that is how to find original function which is in absolute quantity. Okay, and mathematically this problem otherwise we can say how to find derivative function, and in integration how to find antiderivative function. That is, so Newton and Leibniz connect these two problems. Okay, two problems, slopes problem to area problem, instantaneous rate of change to original function. Okay, problem, derivative function to antiderivative function. So differentiation in fact problem is in fact, what is differentiation problem? When given y equal to some function f of x, find rate of change function f prime of x. Okay, so in fact what we do, that is y prime, that is d x of y. Okay, which is in fact f prime of x. Okay, and for integration, when given in integration converse, given rate of change function. For differentiation, given original function y equal to f of x. Okay, find rate of change function. But for integration, given rate of change function, this f of x function, but this is rate of change function, and we find the original function capital F of x. That is, we integrate the rate of change function. Okay, and we find the original function which is capital F of x. Okay, plus some constant c. So this is the underlying ideas what I wanted to say. Okay, thank you.